Right now, something is pouring through your body and you cannot feel any of it. About 100 trillion of them pass through you every second. They arrive from the sun, and they do not slow down, do not warm your skin, do not brush a single nerve. Through every square centimetre of you, an area about the size of a thumbnail, roughly 65 billion of them stream through every second. And yet across your entire lifetime, on average, only one of them will ever actually strike an atom inside you. That particle is called the neutrino. It is one of the most common things in the entire universe. It is also one of the most invisible. Sit with that number for a moment before it slips away. 100 trillion, every second without a single pause, since long before you were born. They poured through you while you slept last night. They are pouring through you now in this exact moment, in the time it takes to read this line. They will pour through you tomorrow and the day after at very nearly the same steady rate. And in a lifetime spent standing inside that flood, the total number that ever touch you, that ever collide with anything you are made of, you could count on a single hand. 1, perhaps. Most of us carry a simple picture of matter, and it feels like plain common sense. You think of solid things as solid. A wall stops a thrown ball. Your hand meets the table and stops there. A particle in that picture is a tiny piece of stuff, and when that stuff meets other stuff, it bounces, or it sticks, or it breaks apart. That picture serves you well for almost everything you will ever touch in your life. It does not describe the neutrino at all. To a neutrino, you are not solid. The wall behind you is not solid, the floor is not solid, and the ground under the floor is not solid, and the whole earth beneath your feet, nearly 8,000 miles of rock and molten metal and pressure, is not solid either. All of it is mostly empty space, and the neutrino treats that emptiness as exactly what it is. It slips between the atoms of your body the way a breath of air moves through an opened doorway. You, to this particle, are a thin drifting mist. The planet is a faint grey smudge. It barely registers as it passes clean through and out the other side. Consider just how empty that is. Imagine you could build a wall out of solid lead. Not a plate, not a vault door, but a wall 1 full light year thick. That is about 5.9 trillion miles of lead, a barrier longer than the distance from here to the nearest star beyond the sun. Now aim a single solar neutrino straight at it. On the far side, the odds are roughly even that it comes right out the other end, untouched, as though the lead had never been there at all, a coin flip. That is what it would take merely to have a fair chance of stopping just one of them. Everything softer than a light year of lead, your body, this room, the entire earth, the sun itself, is essentially transparent to it. Before we go any deeper into what could possibly behave this way, one small thing. If these quiet, strange corners of the universe are the kind of place you like to sit at night, a like or a subscribe genuinely helps this channel keep making them. Deep Space Drift is on Spotify too, if you would rather just close your eyes and listen. That is the whole ask. Now, back to the silent flood. Every second of your life, that count holds steady. 100 trillion, give or take. And it does not matter much where you stand or when. It does not matter if it is the middle of a bright afternoon or the deepest part of the night. During the day, the neutrinos rain down through the sky and pass through the top of your head and out through the soles of your feet. At night, the sun is on the far side of the planet, hidden by the whole width of the earth. You might think that would block them. It does not. At night, those same neutrinos travel straight up through 8,000 miles of solid earth, through the crust, through the mantle, through the searing iron core, and they reach you from below, with almost none of them lost along the way. The planet does not cast a shadow they can hide in. There is no shelter from this rain. There is no roof thick enough, no basement deep enough, no vault heavy enough. It falls on everyone, everywhere, at all hours, and it always has. Think about what that means for a moment. There is nowhere on Earth you could go to escape it. You could climb to the top of the highest mountain, and the flood would be the same. You could descend to the bottom of the deepest mine, a mile of rock stacked over your head, and the flood would still be there, barely thinned. You could seal yourself inside a chamber walled in feet of lead, and it would make no measurable difference at all. This is one of the very few experiences that every human being who has ever lived has shared completely, whether they knew it or not. Every person in every century stood inside the same silent downpour. It passed through the ancient astronomers who charted the stars by eye. It passed through everyone you have ever loved. It is passing through you and through everyone near you right now, at this instant, and not one of you can feel the faintest trace of it. So where does all of it come from? The answer is almost close enough to touch, and it hangs in the sky most days. More than 99% of the neutrinos crossing your body right now were born inside the sun. Not on its glowing surface, but far down in its core, in the crushed and blazing heart of the star, roughly 93 million miles away from where you are sitting. Down there, the sun does the one thing that makes it a sun at all. It fuses hydrogen. Under enormous pressure and heat, the nuclei of hydrogen atoms are pressed together again and again until they merge and become helium. That is the reaction that lights the sun and warms your world and has kept this planet alive for billions of years. And every time that fusion happens down in the core, it throws off neutrinos as a direct byproduct. They are made in that furnace by the countless trillions in the same instant that the sun makes its light. But the neutrinos and the light do not have the same journey out. The light that warms your face is a slow escapee. It is trapped, bounced, absorbed and spat back out over and over in the crushing density of the sun. The neutrino is not trapped by any of that. It is born in the core, and it simply leaves, sailing out through the entire mass of the star as if the star were made of nothing. By the time you notice the sunlight on your skin, the neutrinos that were born alongside it have already crossed the 93 million miles of empty space, arrived at Earth, poured through the ground and the walls and through you, and continued on out into the dark on the far side, still travelling, still barely touching anything, most likely for the rest of time. That is the strangeness we are sitting with. The neutrino is not rare. It is not exotic in the way a black hole is exotic, hidden away in some distant reach of space you will never visit. It is here, in overwhelming abundance, in the very air of the room, in the space between your own atoms, more numerous around you than almost anything else in existence. By sheer count, neutrinos are among the most plentiful particles in the whole universe, and yet for all that closeness, all that constant, staggering presence, they are almost perfectly hidden. You have never seen one. You never will. You have never felt one, and neither has anyone else, not directly, not with any sense your body owns. They are everywhere at once and felt almost nowhere. They fill the world and leave no mark. For most of human history, no one even suspected they were there. There was no gap in anyone's understanding shaped like a neutrino. The particle was not discovered by looking. It was first imagined on paper as a desperate guess to save a broken accounting of energy by a physicist who was so sure it could never be caught that he was almost ashamed to have proposed it. It would take decades of patience, and later some of the largest and strangest machines ever built by human hands, sunk under mountains and frozen into glaciers and dropped to the floor of the sea, before anyone could prove that this ghost was real. That is a story worth telling slowly, and we will get there. But the deeper you look at the neutrino, the more it refuses to fit. Think again about what it is doing. It is passing through solid matter as though matter were an illusion. It carries no charge that you can measure in the ordinary way. It weighs so little that for nearly 40 years the best equations in all of physics insisted it must weigh nothing at all, exactly zero. And those equations turned out to be wrong. It does not glow. It does not push. It does not pull on anything you can detect. It has no surface you could put a ruler against, no colour, no size that any experiment has ever managed to find. It is closer to a travelling ripple than to a tiny ball of stuff. And still, on the rarest of rare occasions, once in an ocean of nothing, it will suddenly behave like a solid, real thing and strike an atom head-on and leave a flicker of light behind. So picture it one more time before we go on. The invisible rain, 100 trillion a second, falling on you day and night, through the mountain and the mine and the whole body of the earth. 65 billion through the thumbnail of skin on the back of your hand every second, and only one in a whole lifetime ever stopping to touch you. A particle so common it is nearly the most abundant thing in the cosmos, and so shy it slides through a light year of lead on a coin flip. Something is here, in enormous numbers right now, and it is almost completely untouchable. That combination should stop you cold. Nothing you can hold in your hand behaves anything like it. And that is the puzzle we are here to sit with. Not the size of the number, though the number is dizzying. Not just the distance it has already travelled to reach you, though it has crossed 93 million miles in the time it takes light to make the same trip. The real mystery is quieter, and it is closer to the bone. What is a thing that fills the universe and touches nothing? What is a thing you cannot feel, cannot see, cannot stop, cannot hide from, and yet that is streaming through your heart and your eyes and your hands at this very second by the 100 trillion? What could it possibly be made of? To move through the whole world like that and leave the world unmarked. Long before anyone caught one, the neutrino existed only as a confession. It began in 1930 with a problem physicists could not explain away. Inside certain radioactive atoms, a process called beta decay was quietly breaking the law. Energy was going missing. You could measure what went into the reaction. You could measure what came out. The two numbers never matched. A small amount of energy simply vanished every single time. This should have been impossible. Conservation of energy is one of the oldest promises in all of science. Energy does not appear from nothing, and it does not slip away into nothing. Yet here, in the decay of a single atom, some of it seemed to leak straight out of the universe. A few physicists were ready to abandon the law entirely. That is how serious it had become. Then a man named Wolfgang Pauli made a wild guess. Picture him in Zurich, a brilliant and famously sharp theorist staring at the same broken numbers as everyone else. He proposed that the energy was not vanishing at all. It was being carried away by a particle nobody had ever seen. This particle would have no electric charge, it would have almost no mass, and it would slip through matter so easily that no instrument on Earth could ever hope to catch it. Pauli knew how strange this sounded. He called his own idea a desperate remedy. In a now famous letter, he wrote to a group of physicists gathered for a conference, addressing them warmly as radioactive ladies and gentlemen, and laid out his invisible particle almost as an embarrassment. He confessed he had done a terrible thing. He had proposed a particle that could never be observed. To a scientist, that sits close to a sin. A thing that can never be detected sits right at the edge of not being science at all. He was so sure it could never be found that he made a bet. A case of champagne wagered against his own idea that no experiment would ever catch it. He believed the particle was real. He simply did not believe anyone would ever prove it. For a few years the little ghost had no name. Then, in 1934, the Italian physicist Enrico Fermi gave it one. He was building a full theory of beta decay, a piece of mathematics that turned Pauli's guess into real physics. He needed a word for the tiny neutral thing at the centre of it. He called it the neutrino. In Italian it means the little neutral one. The name stuck, and it fit. A small, quiet, uncharged nothing, drifting out of every dying atom. And then, for a very long time, nothing happened. Pauli had predicted a particle. Fermi had named it and given it math. But no one could see it. The neutrino stayed exactly what Pauli feared. A ghost that saved the laws of physics and then refused to show its face. Years passed. A world war came and went. The ghost drifted on, uncaught. The problem was always the same. To catch a neutrino, you need it to strike something. but neutrinos almost never strike anything. If you want to trap even a handful of them, you need an enormous flood, far more than any gentle natural source could easily give you. And in the years after the war, humanity had built something that produced exactly that, a nuclear reactor. Two American physicists saw the opportunity. Their names were Cowan and Reines. They understood that a reactor core in the middle of its work throws off a staggering torrent of neutrinos as a byproduct. If neutrinos could ever be caught at all, the best place to wait for one was right beside that roaring source. So in 1956 they went to South Carolina, to the Savannah River nuclear plant. They set up their detector close to the reactor, close enough to sit inside its invisible flood. Picture the machine they built. Large tanks of a liquid called scintillator, a fluid that gives off a tiny flash of light when a particle strikes it just right. Between those tanks, layers of water dosed with cadmium chloride. The water offered the neutrinos protons to collide with. The cadmium was there to catch the aftermath and add a second flash, a delayed echo that would prove the event was real. The idea was patient and precise. A neutrino, on those very rare occasions when it interacts, would strike a proton in the water. That collision would kick out two telltale signals, one after the other, in a tight and specific rhythm. Almost nothing else in nature would fake that exact double beat. So they sat in the dark beside the humming reactor, watching for a pair of flashes that might come only a few times an hour, buried inside a storm of ordinary noise. They watched, they counted, they ran the numbers against every other thing that might trick them, cosmic rays raining from the sky, stray radioactivity, random coincidences, and when they were done, the signal held. The odds that background noise had faked their result came out to about 1 in a million. For a particle that Pauli swore could never be found, that was as close to certainty as anyone could ask. They had done it. After 26 years, the ghost had a footprint. So they sent word to the one man who deserved to hear it first. On the 14th of June in 1956, Cowan and Reines wired a telegram across the ocean to Wolfgang Pauli. They told him, in a few plain words, that his impossible particle had been seen. Pauli's reply was just as short. "Thanks for message," he wrote. "Everything comes to him who knows how to wait." There is a quiet grandeur in that line. He had offered the neutrino as an apology. He had bet against his own creation. And now, a quarter of a century later, the confession had turned out to be true. The formal announcement came soon after. Their results were published in the journal Science on the 20th of July in 1956. Count the years carefully, and the timing is almost poetic. Pauli had floated his desperate remedy in 1930. The proof arrived in the summer of 1956, 26 years later, almost to the very day. A prediction made in near despair, confirmed a generation later, using the highly radioactive heart of a nuclear reactor as bait. Eventually, the highest honour in science came calling. In 1995, Frederick Reines was awarded the Nobel Prize in Physics for catching the neutrino. It had taken decades for the work to be fully honoured, and by then it could only honour half of it. Clyde Cowan, his partner in the dark beside the reactor, had died in 1974. The Nobel Prize is not given after death, so Reines accepted the prize for a discovery that two men had made together, and he stood there without him. Sit with the shape of that story for a moment. A particle proposed by a man who was certain it could never be found. A name given by another who never saw it. A quarter-century of silence. Then a flash of light beside a reactor, a telegram, and a case of champagne finally lost the very idea he had doubted. The neutrino had gone from a desperate guess to a confirmed piece of reality, one of the fundamental building blocks of the universe. And yet, catching it changed almost nothing about how impossible it feels. Confirming the neutrino did not make it any less of a phantom. It still carried no charge. It still weighed almost nothing. It still passed through the entire planet as though the planet were not there. Cowan and Reines had proved that it existed. They had not made it any easier to hold, so the deeper mystery only sharpened. It was one thing to know the neutrino was real. It was another thing entirely to say what it was. A particle with no charge and almost no mass and no willingness to touch the world around it. Something that streams through your body and through the earth and through a light year of solid lead without so much as a nudge. Pauli had summoned it to balance an equation. He had never really explained it. So the real question tonight is not how something so common can be so completely invisible, but what a neutrino actually is. So the real question tonight is not how something so common can be so completely invisible, but what a neutrino actually is. And the first surprise is how little there is to it. A neutrino is not a tiny machine with parts inside. It is not built from anything smaller. When physicists call it a fundamental particle, they mean that word without any softening. You can take a proton and break it apart. Inside you will find quarks, 3 of them, bound together by a force so fierce it takes real violence to tear them loose. A neutrino has no inside like that. There is nothing to open. There is no hidden machinery, no smaller grain waiting to be found. It sits at the very bottom of the list of things the universe is made from, one of the handful of pieces that are not made of anything else. It belongs to a family of particles called the leptons, and you already know one member of that family very well because you are built from them. The electron is a lepton. Every electron humming around every atom in your hands, in the chair beneath you, in the walls of the room, is a cousin of the neutrino. They come from the same branch of the family tree of matter. The electron and the neutrino are close relatives, born of the same rules, and yet they could hardly behave more differently. The whole story of the neutrino is really the story of that difference, and the difference begins with a single number. That number is charge. An electron carries a negative electric charge. That one property is the reason the electron does almost everything it does. It is why the electron clings to the nucleus of an atom. It is why atoms lock together into molecules. It is why the ink of the world holds its shape, why water is wet, why your skin does not simply sink through the surface you're resting on. Electric charge is the handle that one of nature's great forces uses to take hold of matter. That force is called the electromagnetic force, and it is everywhere in your life. Light is the electromagnetic force. Chemistry is the electromagnetic force. Warmth on your face is that same force. Touch itself, the feeling of anything solid pressing back against you, is charged particles refusing to overlap. Almost every sensation you have ever had traces back to that one force at work. Now hold the neutrino up against all of that. A neutrino carries no charge at all. Not a small amount, not almost none, exactly zero. And with no charge there is no handle for the force to grip. The electromagnetic force reaches out for a neutrino and closes on nothing. Light does not bend it. Magnets do not steer it. Chemistry cannot bind it. It cannot be pushed, pulled, heated or stopped by the force that shapes nearly everything you will ever experience. Even the name remembers this. The physicist Enrico Fermi named it the neutrino, Italian for the little neutral one. Neutral because it answers to none of it. It slips past the whole electric world as though that world were not even there. There is a second great force living inside every atom, and the neutrino ignores that one too. It is called the strong nuclear force. It is the glue at the centre of matter, the thing that binds protons and neutrons into a tight knot in the nucleus of every atom. At close range it is the most powerful force in all of nature, strong enough to hold protons together even as their charges scream at each other to fly apart. But the strong force only grips particles built from quarks. It only pulls on things that have that inner structure. The neutrino has no quarks inside it. So the strongest force in the universe, the one that holds the heart of all matter together, feels nothing when a neutrino drifts past, and the neutrino feels nothing in return. So think carefully about what that leaves. There are 4 fundamental forces in nature, and for the neutrino 2 of them simply switch off. The electromagnetic force, gone. The strong force, gone. Only 2 remain that can touch a neutrino at all. The first is gravity. Gravity pulls on everything that carries mass, so it does reach the neutrino. But a neutrino weighs so vanishingly little that its gravity is nothing you could ever measure on any human scale. That leaves one last force, and it is the only one that truly matters here. It is the weak nuclear force. The weak force is the single doorway through which a neutrino can knock against the ordinary world. It is the only way a neutrino ever announces that it exists. And the trouble is right there in the name. The weak force is weak. Over the distances inside an atom, it is far, far feebler than electromagnetism, and it reaches across only an almost impossibly short range. For a neutrino to interact through it, the neutrino must pass so close to the very centre of a particle, so precisely on target, that the odds of it happening are almost nothing. That is the whole secret of the neutrino in a single idea. It carries no charge for the strong forces to grab, and the one force that can touch it barely reaches at all. That is why a neutrino can cross an entire planet and never once noticed the planet was in the way. There is not just one kind of neutrino either. There are 3 of them. Physicists call the 3 kinds flavors, a light word for a deep distinction. There is the electron neutrino, there is the muon neutrino, and there is the tau neutrino. Each one is tied to a heavier charged partner from the lepton family. The electron neutrino travels alongside the electron you already know. The muon neutrino is paired with the muon, a particle that behaves like a heavier short-lived electron. The tau neutrino goes with the tau, heavier still. 3 neutrinos, 3 partners, 3 matched pairs woven through the deepest structure of matter, and of all of them, the ones pouring through your body from the sun at this very moment are almost entirely electron neutrinos made at the nuclear fire at the sun's core and thrown outward in unimaginable numbers. And now comes the strangest chapter of all, the one that broke the rule book. For nearly 40 years, the finest theory physics has ever produced said that a neutrino should weigh exactly nothing. That theory is called the Standard Model. It is the most tested, most confirmed set of equations in the entire history of science. It predicts the behavior of the subatomic world with a precision so fine it can feel like reading the mind of nature. And this triumphant theory said, plainly and confidently, that the neutrino must be massless, weightless, like a particle of light itself which has no mass at all. For decades the neutrino sat in that weightless box, and no experiment on Earth could pry it out. Then, at last, one did. Deep underground, shielded from the noise of the surface, physicists watched neutrinos quietly change from one flavor into another as they flew, an effect they call oscillation. A neutrino born as one kind arrives somewhere else as another, and that shape-shifting is only possible under the deepest laws of physics if a neutrino carries mass. If its mass were truly zero, it could never change. The oscillation proved the mass was real. The equations had been wrong. One of the most successful theories ever written had a crack running clean through it, and the neutrino is the crack. So the neutrino has weight after all. But how much? Here the numbers turn almost absurd. In 2025, an experiment in Germany called Katrin set the tightest limit ever measured on that weight. It found that the mass of the electron neutrino is no more than 0.45 electron volts. An electron volt is a unit so small it is used to weigh single particles one at a time, and for comparison, hold up the electron again, already one of the lightest things known to carry any mass at all. The electron weighs about 511,000 electron volts. The neutrino weighs, at the very most, less than half of one. That makes a single neutrino at least 1,000,000 times lighter than a single electron. Sit with that ratio for a moment, because it is hard to hold in the mind. If an electron were the weight of 1 grain of sand, the neutrino would be lighter than 1,000,000th of that grain. It is trying to weigh a whisper against a boulder, and Katrin did not reach the number by putting a neutrino on a scale. No scale could ever do it. Instead, the experiment watched about 36 million electrons come flying off decaying radioactive tritium, gathered over 259 days of patient counting, and measured the energy of each one with fanatical care. They were looking for the faint shadow the neutrino's mass leaves behind in that energy, a tiny missing sliver at the very edge. Even after all of it, physicists still do not know the neutrino's exact weight. They know only that it is real, that it is not zero, and that it is smaller than almost anything else in the whole of nature. And this is where the neutrino stops feeling like an object at all. It carries no charge. It carries almost no mass. And as far as any experiment has ever managed to tell, it has no size. There is no radius you could measure. There is no surface you could press a finger against. No inside, no outside, no structure of any kind hiding within it. It behaves the way physicists say a perfect point behaves, a place with no width, a thing that takes up no room whatsoever. There is genuinely nothing to look at. No colour, because colour is made of light, and light slides right past it. No shape, because shape needs edges, and the neutrino has none. It is far closer to a mathematical ripple than to a pebble, a faint wave that only now and then, very rarely, behaves like a solid thing at all. This is the nearest thing physics has ever found to a phantom. It is present in every cubic inch of space around you right now. It is streaming through the ceiling, through the floor, through the mattress, through your own chest by the trillions every second, and felt almost nowhere. Not because it is hiding from you, not because it is cloaked or shy. It goes unfelt because there is so terribly little of it for the ordinary world to catch on to. A particle with no charge and almost no mass gives ordinary matter almost nothing to grab, and that, more than anything, is why it can pass straight through you. A particle with no charge and almost no mass gives ordinary matter almost nothing to grab. That, more than anything, is why it can pass straight through you. But there is one thin thread left. There is one force that can still, just barely, reach a neutrino. It is called the weak nuclear force, and it is the reason a neutrino is not quite a perfect ghost. The weak force is real. It is one of the 4 fundamental forces that hold the universe together. But it is faint, and it has almost no reach. It only works across distances far smaller than the nucleus of an atom. So a neutrino can only feel another particle if it passes almost exactly through the heart of it, not near it, through it. Physicists have a word for how likely that is. They call it the cross-section. Think of it as the size of the target a particle holds up to the world. A big cross-section means an easy hit. A tiny cross-section means a particle almost impossible to strike. The neutrino has one of the smallest cross-sections in all of physics. To the rest of matter, it is barely a target at all. It is a needle trying to be hit by another needle, in the dark, across a room the size of an atom. So consider what that means in a real number. Imagine building a wall of solid lead. Not a foot of it, not a mile of it. A wall of lead 1 full light-year thick. That is about 5.9 trillion miles of solid metal, a barrier longer than the distance to the nearest star. Now fire a single solar neutrino at it. On average, that neutrino has only about a coin flip's chance of being stopped before it reaches the other side. Half of them would sail clean through a light year of lead as if it were an open window. Sit with that for a moment. There is nothing you own, nothing you could ever build, that a neutrino treats as solid. Your body, the floor beneath you, the whole rock of the planet under your feet, all of it is more transparent to a neutrino than the clearest glass is to light. If you like these quiet walks through the physics of the very small, a like or a subscribe genuinely helps this channel drift into more ears, and every episode is on Spotify too if you fall asleep before the end. Now turn that same fact around and point it at your own body. Roughly 100 trillion neutrinos from the Sun are passing through you every second. About 65 billion of them cross every square centimetre of you, an area no bigger than your thumbnail, in that same single second. This is happening right now as you lie here. It has never once stopped, and yet the odds that any single one of those neutrinos will strike an atom inside you are about 1 in 10,000 billion. Written out, that is a 1 followed by 22 zeros. The odds are so long that they run past a single day, past a year, past a decade. Add them up across an entire human life, across every second of every night you have ever slept, and every day you have ever walked in the sun. In all of that time, on average, only one neutrino will ever physically collide with a single atom somewhere inside your body. One, across a whole lifetime. Out of a flood that never pauses, one solitary touch, and you will never feel it happen. More than 99% of that flood was born in one place. It came from the core of the Sun, about 93 million miles away, forged in the same hydrogen fusion that makes the Sun shine. And here is where the neutrino does something that should stop you cold, because it reveals just how little it interacts with anything. When fusion happens deep in the Sun's core, it makes two things worth watching. It makes light in the form of photons, and it makes neutrinos. They are born in the same reactions, in the same instant, in the same crushing centre of the star. But their journeys out could not be more different. The photon has a nightmare ahead of it. The Sun's interior is not empty. It is a wall of superheated plasma, packed so dense and so hot that light cannot travel in a straight line for more than a tiny fraction of an inch before it slams into a charged particle. It is absorbed. It is spat back out in a random direction. Then it hits something again, and again, and again, billions upon billions of times. The photon does not fly out of the Sun. It staggers, blind and drunk, in a random walk, bouncing in every direction, taking a step forward and half a step back. Physicists estimate that a single photon born in the Sun's core takes tens of thousands of years to fight its way out to the surface. Tens of thousands of years to cross a distance light could cover in about 2 seconds if the path were clear. Now watch the neutrino, born in that exact same reaction, in that exact same core. It feels almost none of that plasma. The charged particles that trap light for millennia are, to a neutrino, barely there. It does not bounce, it does not scatter, it flies out of the Sun in a nearly perfect straight line, and it clears the entire star from the fusing core all the way out through the crushing weight of the plasma and into open space in about 2.3 seconds. Hold those two numbers next to each other, tens of thousands of years for the light, 2.3 seconds for the neutrino. Same star, same reaction, same distance to travel. The only difference is how strongly each one grips the matter in its way. The photon grips hard and pays for it with millennia. The neutrino barely grips at all, and it is gone before you could finish a slow breath. The sunlight warming your face today left the sun's surface about 8 minutes ago, but the energy inside it began its journey out of the core before the first cities were ever built. The neutrinos passing through you left that same core less than a fortnight ago. So that is the impossible arithmetic of a neutrino passing through you. 100 trillion a second, day and night, cradle to grave, and you never register a single one. No pressure on your skin, no warmth, no sound, no shadow. A silent river with no banks pouring through the room, through the bed, through your closed eyes and the bone behind them, and out the far side into the ground, and it asks nothing of you and leaves nothing behind. You have been standing under this waterfall your whole life, and you have never once felt a drop. And yet, very rarely, the neutrino does touch something, and when it does, it leaves behind the one visible sign it is capable of making. It is worth understanding, because everything humanity knows about catching these particles hangs on it. Once in a great while, a neutrino passing through matter scores a direct hit. It strikes a proton or a neutron dead center, close enough for the weak force to bite. In that collision, it knocks loose a charged particle and sends it flying, and that freed particle comes tearing away at almost the speed of light in a vacuum. Here is the strange part. Light itself slows down when it travels through water or through ice. It moves noticeably slower there than it does through empty space. So the charged particle, for a brief flash, can actually be moving faster than light moves through that particular water or that particular ice. Nothing outruns light in a vacuum, but something can outrun light in water. And when a charged particle does that, it drags a shockwave of light behind it, a faint cone of eerie blue glow spreading out in its wake. Physicists call it Cherenkov radiation. It is the same ghostly blue light you may have seen photographed in the water around the core of a nuclear reactor. That blue is not a warning colour someone chose. It is the literal glow of particles crossing that speed threshold, light itself struggling to keep up. That single, faint, blue cone is the whole visible signature of a neutrino event. Not a bang, not a spark you could ever see with your eyes. A brief flicker in perfect darkness, a one-frame flash lasting a fraction of a second, buried in an ocean of nothing. That is all a neutrino ever offers as proof it was here, and it offers it only a handful of times, even inside a target the size of a building, even across a whole day of waiting. There is one last thing to understand, and it is the deepest strangeness of all. It is not a limit of our machines. It is a limit written into reality itself. You might think that with better instruments, we could learn to predict exactly which neutrino out of that flood will be the one to strike an atom inside you. We cannot. And it is not because we are not clever enough yet. It is because the answer does not exist to be found. The rules of quantum mechanics do not deal in certainties about single particles. They deal only in probabilities across enormous crowds of them. Physics can tell you, with beautiful precision, that about one neutrino in 10,000 billion will interact. It can tell you the odds to as many decimal places as you like, but it can never tell you which one. It cannot point to a particular neutrino in that river pouring through you and say, that one, that is the one that will touch you tonight. The information is not hidden from us. It is simply not part of how the universe is built. Each neutrino carries only a chance, a whisper of possibility, and whether it acts on that chance is decided by nothing you or anyone could ever measure in advance. You can know the crowd perfectly and know nothing at all about the individual. That uncertainty is not a gap in the map. It is the shape of the ground. So this is what the neutrino truly is, in the way it moves through the world. A particle with almost no target to offer. A traveller that treats a light year of lead like open air and treats you like nothing at all. A messenger that outruns its own light out of the sun by tens of thousands of years because it refuses to be held. A flood of 100 trillion a second that touches you once in a lifetime, if that, and slips away without a trace. And a mystery so complete that the universe itself keeps no record of which one will ever stop, which leaves the people who want to study these particles with a strange and daunting problem. If a neutrino will pass through a light year of lead and touch a whole human body only once in 80 years, then how could you ever hope to catch one on purpose? You cannot wait for luck in a teacup of water. You cannot line a small box with sensors and expect a signal. The odds are simply too long. The only way to beat those odds is to gather an absurd amount of matter into one place, and then wait in the dark for that one flash of blue. So think about what actually happens on that one rare occasion when a neutrino stops being ghost. It does not glow. It does not announce itself. What it does is strike a single proton or neutron inside an ordinary atom. And in that collision, just it hands over its energy to something we can see. The neutrino knocks loose a fast charged particle. Usually that particle is an electron or its heavier cousin, the muon. The neutrino itself may carry on, changed and quieter. But the charged particle it left behind is now racing through the water at tremendous speed, and that is the thing we can catch. Here is the strange part. That charged particle is moving faster than light. Not faster than light in empty space. Nothing does that. But light slows down when it travels through water. In a tank of water, light crawls along at only about 3/4 of its speed in a vacuum. The little particle knocked loose by the neutrino is not bound by that slowdown. So for a brief moment inside the water, the particle outruns the light around it. It is moving faster than light can move in that medium. When that happens, the water answers. It answers with a shock wave made of light. You already know the shape of this. A boat cutting across a lake pushes up a V of water behind it, because the boat is moving faster than the ripples it makes. A jet crossing the sky faster than sound drags a cone of pressure behind it, and you hear it as a boom. A charged particle tearing through water faster than light can travel there does the same thing, only the wake it leaves is not water and not sound. The wake is a cone of pale blue light. Physicists call it Cherenkov radiation. It is faint, it is brief, and it is very, very blue. You have almost certainly seen this colour before without knowing what it was. It is the same unearthly blue that glows around the core of a nuclear reactor sitting underwater. That deep pool light, the colour of a swimming pool lit from a source that should not be there, is Cherenkov radiation. Charged particles from the reactor are racing through the water faster than light can, and the water glows. When a neutrino leaves its mark in a detector tank, it leaves that exact same blue. One tiny silent cone of it, a single flicker of reactor blue in a place buried in total darkness. Now catch your breath for a moment, because that flicker is almost nothing at all. It is a faint ring of light lasting a fraction of a second. If you were floating inside the tank, you would never notice it. So how do you photograph something that faint, that fast, that rare? You line the walls with eyes. Picture the inside of the Super Kamiokande detector in Japan. It is a cylinder of stainless steel, 128 feet across and 136 feet tall, holding 50,000 tons of the purest water on Earth, and covering nearly every inch of its walls are more than 13,000 photomultiplier tubes. Each one is a large golden bulb, an eye tuned to catch a single particle of light, 13,000 of them, staring inward at the black water, waiting. They do nothing for hours. Then the blue cone sweeps across them, and a patch of those eyes lights up one after another in a ring. That ring is the whole picture. But the real trick is not that the tubes see the light. It is when each one sees it. The blue cone spreads outward like a slow searchlight, and it reaches one wall of tubes a hair before it reaches another. We are talking about differences of billionths of a second. A photomultiplier tube on one side of the tank registers the flash a few nanoseconds before a tube on the far side. Each tube stamps the exact instant the light touched it. Thousands of those tiny timestamps read together form a kind of map. From the shape of the ring and from the razor-thin ordering of which eye blinked first and which blinked last, physicists can rebuild the path the charged particle travelled. They can point in the dark and say the particle went that way, and that direction is the prize. Because the charged particle was flung forward along roughly the same line the neutrino was travelling when it struck. Reconstruct the particle, and you have reconstructed the neutrino's flight path. You have an arrow. Follow that arrow backward, out of the tank, up through thousands of feet of rock, off the planet, and it points at wherever the neutrino was born. That is how a tank of water becomes a telescope. Not a telescope for light, which any dust cloud can block, but a telescope for ghosts, which nothing blocks. This is why physicists can say a neutrino came from the sun. The arrow points at the sun. It is why, when a star died in the Large Magellanic Cloud, detectors could tie that burst of particles to that explosion. And it is why, in 2017, a single high-energy neutrino caught with this same blue light method could be traced back along its arrow to a specific object in the sky, a flaring black hole jet called a blazar named TXS 0506+056, roughly 4 billion light-years away. One flash of blue in a tank on Earth and an arrow reaching back 4 billion years to a monster at the center of another galaxy. That is what timing thousands of eyes can do. But hold on to how rare that flash is, because rarity is the whole problem. You have a detector the size of a downtown building, 50,000 tons of water, 13,000 eyes. And even with all of that sitting in a flood of trillions upon trillions of neutrinos pouring through it every second, the machine records only a handful of clean events on a given day. A handful. Out of a river you cannot even imagine the size of. A mere few particles a day leave a mark clear enough to read, so most of the tank's life is spent seeing nothing. The eyes stare into black water. The water sits in perfect stillness under the mountain. Hour after hour the tubes report darkness, darkness, darkness. Then, once in a great while, for a sliver of a second, a single blue cone blooms somewhere in the dark and sweeps across a patch of the golden eyes. They record it. They stamp their times. And then the tank goes black again and the waiting starts over. Think about what that means for the pictures these machines make. A neutrino image is not a photograph in any ordinary sense. It is one frame. One frozen instant of pale blue light pulled out of an endless reel of black. There is no video of a neutrino, no glowing trail you could follow with your eye. There is a flash, and there is the memory of a flash, held in thousands of timestamps, and from that alone the direction is drawn. A single frame of blue in an ocean of nothing, and the whole science is built on reading those frames one at a time, and every one of those frames is a translation. A ghost that ignores nearly all matter, that carries no charge, that leaves no wake in ordinary stuff, is coaxed for one instant into leaving a wake in water. The neutrino trades a scrap of its energy to a charged particle. The charged particle outruns the light in the water. The water glows blue. The eyes on the wall catch the glow. The times are compared. The arrow is drawn. And a thing you could never touch or see becomes, at the end of that chain, a direction on a map and a source in the sky. It is a beautiful and slightly eerie way to see. You are not looking at the neutrino. You never look at the neutrino. You look at the bruise it leaves in the water, the faint blue echo of a particle that has already moved on. Everything the detector knows, it knows second hand, from that one flicker of reactor-coloured light, which tells you exactly how much water, how many eyes, and how much patience it takes to see even second hand. A single clean frame a few times a day, drawn out of trillions of silent passes, means the odds are stacked against you at a scale that is hard to hold in your mind. You cannot improve those odds by making the instrument cleverer. There is no clever. There is only more. More water, more ice, more eyes, more tons of pure stillness sitting in the dark waiting for the blue. To catch even a single one of these ghosts, you cannot build something delicate. You have to build something monstrous. To catch even a single one of these ghosts, you cannot build something delicate. You have to build something monstrous. You have to go underground into the dark, and you have to think big. Not big like a room, big like a cathedral carved out of the inside of a mountain. Picture that cathedral now. It sits about 300 feet under Mount Ikeno in Gifu Prefecture in Japan. It is called Super Kamiokande. It is a single stainless steel cylinder, 128 feet across and 136 feet tall, taller than a 10-story building, buried where no sunlight has ever reached, and it is full of water, about 50,000 tons of it. Not ordinary water. This is the purest water on Earth, filtered so completely that it is almost eerie, so clear you could see for hundreds of feet through it if there were any light down there to see by. There is not. The tank sits in total blackness, all day, every day, year after year. Now look at the walls. They are not smooth. They are studded with more than 13,000 glass eyes, golden and round, each one a photomultiplier tube. A photomultiplier tube is a light amplifier. It takes a flicker so faint that no human eye could ever register it, and turns that flicker into a signal a computer can read. 13,000 of them, all facing inward, all staring into the water, all waiting. They are waiting for the blue flash. When a neutrino out of trillions upon trillions finally strike a proton or a neutron in that water, it knocks loose a charged particle. That particle races through the water faster than light itself, moves through water, and it drags behind it a cone of faint blue light. That light is called Cherenkov radiation. It is the same ghostly blue you have seen glowing around a nuclear reactor core. In Super Kamiokande, it is the entire signature of a neutrino. One ring of blue, gone in less than the blink of an eye, caught by the golden eyes on the wall. Before we go on, if this is settling into your ears the way it should, a quiet like or subscribe helps this channel keep making these. We are on Spotify too, if you drift off better with sound in the dark. That is all. Back to the water. To understand why anyone would build such a thing, you have to go back further and deeper to a gold mine in South Dakota. There, 4,150 feet underground, a scientist named Raymond Davis Jr. built the first machine that ever caught a neutrino from the sun. His detector was not water. It was a 100,000-gallon tank of dry cleaning fluid, a chemical called perchloroethylene. It ran from 1970 to 1994, a quarter of a century in the dark. And the idea was simple, almost strange. Every so often, a solar neutrino would strike a chlorine atom in that fluid and turn it into a single atom of radioactive argon. Davis would then flush the enormous tank and with painstaking care count those individual argon atoms, a handful at a time, from a swimming pool of fluid the size of a small building. He was quite literally counting ghosts one by one. And here is where the story turns, because Davis found something wrong. He counted the neutrinos coming out of the sun, and there were not enough of them. Not by a little. He was seeing only about a third of the number that the physics of the sun said had to be there. 2/3 of the expected neutrinos were simply missing. This was not a small error you could shrug off. The sun is the most studied object in the sky, and the equations describing its core were solid, yet the neutrinos would not add up. This shortfall got a name. It became the solar neutrino problem, and it sat there, unsolved, nagging at physicists for 3 decades. Either something was wrong with our understanding of the sun, or something was wrong with our understanding of neutrinos. Nobody could say which. Sit with that for a moment, because this is the part worth slowing down for. For 30 years, one of the most careful measurements in all of science kept coming back wrong, and no one could fix it. 2/3 of the ghost vanished somewhere between the sun and South Dakota, and the answer, when it finally came, was stranger than anyone had guessed. The answer came from the cathedral under the mountain and from a second machine a world away. Super Kamiokande began watching the sky and the sun from 1986. And in a mine in Ontario, Canada, another detector switched on in 1999, the Sudbury Neutrino Observatory. Between them, these two machines finally solved the puzzle that had haunted physics since Davis first started counting argon atoms. The neutrinos were not missing at all. They were in disguise. Here is what nobody had understood. There are 3 kinds of neutrino, 3 flavors, and they are called the electron neutrino, the muon neutrino, and the tau neutrino. The sun produces electron neutrinos. Davis's tank and every detector like it could only see electron neutrinos. So when 2/3 of them seemed to vanish off the way to Earth, everyone assumed they were simply gone. They were not gone. On the journey from the sun to your part of the sky, they had changed. An electron neutrino mid-flight quietly shifts into a muon neutrino, or a tau neutrino, and then perhaps back again. Physicists call this oscillation. The neutrinos flicker between identities as they travel, like a single note sliding between 3 different pitches. Davis was only ever hearing one of the 3 notes, so he heard about 1/3 of the music. The rest was still playing. He just could not detect it. Super Kamiokande and the Sudbury Observatory could. Sudbury in particular was built to catch all 3 flavors, not just one, and when it counted the full set, the numbers finally clicked into place. The total matched what the sun should produce. Nothing had ever been missing. The neutrinos had simply been changing their nature in mid-stride, all the way across 93 million miles of empty space. And this is where the story stops being about counting and becomes about something deeper, because oscillation carries a hidden consequence. A particle can only flicker between identities like this if it has mass. If neutrinos truly weighed nothing at all, as the equations had long insisted, they could not oscillate. They would arrive exactly as they left. The fact that they change proves, all on its own, that a neutrino must weigh something. Tiny beyond imagining, but not zero. This is why oscillation was not just a clever fix for an old puzzle. It cracked open the standard model itself, the most tested theory in all of physics, and showed that one of its firm predictions was wrong. The 2 men who led those discoveries, Takaaki Kajita of Super Kamiokande and Arthur MacDonald of Sudbury, shared the Nobel Prize in Physics in 2015. Not for building bigger tanks, for proving that the ghost has weight, that a particle which barely touches anything, which slips through a light year of lead, which you cannot hold or see or feel, nonetheless tips the scale by the faintest amount above nothing. A 30-year mystery, buried in a gold mine, ended with a rewrite of the rulebook of matter. Once you know what the flash looks like, and once you know the ghosts are real, the only question left is how big a net you are willing to build. And the answer, it turns out, is very big indeed. Because there is a machine larger than any tank, larger than any mine, larger than anything you would think to call a machine at all. It is called Ice Cube, and it sits at the bottom of the world. Go to the South Pole, go to the Amundsen Scott Station, where the wind never stops and the ice runs miles deep. Ice Cube is not built out of steel or water. It is built out of the ice itself. More than 5,160 optical sensors hang frozen inside a full cubic kilometre of ancient Antarctic ice. Picture that. A cube of solid ice, a little over half a mile on every side and threaded all through it, like beads on strings, more than 5,000 glass eyes staring into the frozen dark. The sensors sit deep, between roughly 4,157 and 8,038 feet down, well over a mile beneath the surface at their lowest. The way they got there is almost harder to believe than the machine. You cannot dig 1.5 miles into a glacier with a shovel, so they melted the ice. Engineers built enormous hot water drills, jets of scalding water under pressure, and they used them to bore holes straight down into the ice sheet, more than 1 mile deep, one hole at a time. Into each melted shaft they lowered a long string of sensors down into the black water at the bottom of the world. And then they waited. The cold did the rest. The Antarctic ice, the coldest, clearest, most light-free natural material anywhere on this planet, closed back around the sensors and froze them into place, permanently. They are down there now, locked in the glacier, and they are not coming back out. The ice is both the freezer and the detector. When a neutrino strikes an atom in that ice and flings out its cone of Cherenkov blue, the frozen dark carries that flash cleanly to the waiting eyes. That is the scale humanity has reached for. A tank of the purest water on Earth, 1/2 mile under a Japanese mountain. A pool of dry cleaning fluid nearly 1 mile down a gold mine. A cubic kilometre of Antarctic glacier wired with 5,000 sensors and frozen solid. These are among the largest scientific instruments ever built. Cathedrals of steel and stone and ice, sunk into the deepest, darkest, quietest places we could find. And here is the thing you have to hold on to as you drift. For all that size, for all that ambition, these monstrous machines are almost always idle. The blue flash they exist to catch does not come in a flood. Even in a detector the size of a skyscraper, even inside a full cubic kilometre of ice, a real neutrino event registers only a handful of times a day. You build the largest instrument in the world. You sink it 1/2 mile under a mountain or 2 miles under the sea. You wire it with thousands of eyes, and then you sit in the dark and wait for a flicker that comes a few times between one sunrise and the next. The rest is silence and stillness and pure black water, holding its breath. That is the price of catching a ghost. Not delicate instruments, enormous ones, mostly empty, mostly quiet, watching for the rare accident where a particle that ignores nearly everything finally, briefly, touches something. Consider what it takes to catch even one of these particles at its most extreme. Off the southern coast of Sicily, on the floor of the Mediterranean Sea, there is a machine listening in the dark. It is called KM3Net, and one of its arms, the telescope known as ARCA, is anchored roughly 2 miles underwater. Down there, the water is black and still and cold. Strings of glass optical sensors hang from the seabed, tethered like kelp, rising up through the deep. Each sphere waits for a single flash of blue light. That flash is the only sign that a neutrino has passed through and, for once, touched something on its way. 2 miles of seawater sit overhead as a shield. All that water blocks the ordinary clutter of cosmic rays that would otherwise blind the senses. Only the rarest, most penetrating particles make it that deep with anything left to say. So the sea itself becomes part of the detector. The water is both the filter and the target, and on one occasion the deep caught something no instrument had ever caught before. The event has a plain technical name, KM323-2-13A. It was first registered on the 13th of February 2023, though the collaboration did not announce it to the world until February of 2025. In those 2 years, physicists checked it, doubted it, and checked it again, because the number attached to it was almost too large to believe. The particle carried an energy of about 220 PeV. Written out, that is roughly 220 quadrillion electron volts. It was about 30 times more powerful than any neutrino ever detected before it. Sit with that figure for a moment. 30 times more energetic than the previous record holder. Not a small step past the old mark, but a leap clean over it. A single ghost particle arrived at the bottom of the sea, carrying more energy than physicists had ever seen one carry, and it announced itself with one faint cone of light in the abyss. Everything humanity knows about that particle comes from that one flicker, read by sensors 2 miles down. And here is the part that keeps physicists awake. No one is sure where it came from. When a neutrino arrives with that much energy, it points back towards something violent enough to have made it. Some engine in the deep sky running hotter than anything nearby. The trouble is that several suspects fit, and none of them confess. One candidate is a blazar, the jet of a supermassive black hole aimed almost straight at Earth. Another is a gamma-ray burst, the brief and blinding death cry of a massive star. And a stranger idea lingers at the edge of the list. Some suggest the particle may be a relic, a fossil left over from the earliest moments of the universe itself. As of the announcement, no single source has been confirmed. The most energetic neutrino ever caught remains an unsigned message. That is the strange bargain of this whole field. You build an instrument at the limit of what engineering allows, you sink it to the floor of the sea, and it hands you a record-breaking number wrapped around a question you cannot yet answer. At the other end of the earth, a rival machine keeps its own vigil in the ice, the same kind of listening in a very different silence. And in February of 2026, that machine took a step forward. IceCube, frozen into the Antarctic ice near the South Pole, completed its first major sensor upgrade since construction on it began back in 2005. 21 years of watching, and only now the first serious refit of its eyes. New sensors lowered into the ice to sharpen what the array can see. It is a modest phrase, a sensor upgrade, but it points at something much larger. That upgrade is a stepping stone toward a future observatory called IceCube Gen 2. The plan for Gen 2 is not to nudge the detector a little bigger. It is to increase the instrumented volume by a factor of 8. 8 times the ice, watched at once. Think about what that means for a particle this shy. The odds that any single neutrino interacts are so absurdly small that the only way to catch more of them is to watch more matter. You cannot make the neutrino more willing. You can only widen the net. So the answer, again and again, is scale. More water, more ice, more tons of clear material held in the dark, waiting for the one particle in an unthinkable number that finally stops. And there is a second kind of extreme instrument in this story, one that does not hunt for the most violent neutrinos at all. It hunts for the faintest possible whisper the particle leaves behind, and it does so to answer a different question. Not where did you come from, but how much do you weigh? That machine is Katrin in Germany, and what it did is a feat measured almost entirely in numbers. To weigh something that barely exists, Katrin did not weigh a neutrino directly. It cannot. Instead, it watched electrons. Specifically, it tracked the energy of about 36 million electrons, each one flung out by the radioactive decay of tritium, a heavy form of hydrogen. When tritium decays, it releases an electron and a neutrino together, and the two of them share a fixed budget of energy between them. If the neutrino carries even the tiniest sliver of mass, it steals a matching sliver from the electron. So the mass of the neutrino, that near nothing, hides in the exact upper edge of how much energy the electrons are allowed to have. To read that edge, you need an enormous count of electrons and exquisite patience. Katrin gathered its 36 million electrons over 259 days of data collection, spread across the years 2019 to 2021. That became the largest dataset of its kind ever assembled for this measurement. And from all of it, from millions of decays clocked one by one, came a single ceiling. The mass of the electron neutrino is no more than 0.45 electron volts. That is not the neutrino's weight. It is the fence beyond which the neutrino's weight cannot go. Even a fence that low is a triumph because of what it is measuring against. Recall the comparison. An electron, already one of the lightest particles that has any mass at all, weighs about 511,000 electron volts. The neutrino comes in at less than half of one. It is at minimum something like 1,000,000 times lighter than the electron, and Katrin pinned that ceiling by clocking the energy of individual particles for the better part of a year. Set these 3 feats side by side and a pattern shows itself. 2 miles of seawater to catch the most energetic ghost on record. A cubic kilometre of ice, soon perhaps 8 times that, to gather the rare few that stop in the frozen dark. And 259 days spent counting 36 million electrons to weigh a particle that weighs almost nothing. Each of these is an instrument pushed to a physical extreme. Each was built to weigh, or to clock, or to place, something that barely interacts with the world at all. And notice what the numbers have in common. 220 quadrillion electron volts of energy in one particle, a ceiling of less than half an electron volt on its mass, a factor of 8 waiting in the ice, 30 times past the old record. These are not round, comfortable figures. They are the readouts of machines straining at the edge of the possible, reporting back on something that would rather not be measured. The neutrino gives up almost nothing willingly. Every number here was pried loose by an instrument bigger, colder, deeper, or more patient than the one before it. There is a quiet humility in all of it. You cannot corner a neutrino. You cannot hold one still. You can only build something vast enough, and still enough, and dark enough, that now and then one of them betrays itself with a flash or a stolen sliver of energy. The sea does the catching. The ice does the catching. A slow tally of electrons does the weighing. The particle itself never cooperates. It only occasionally leaves a trace. But that trace is enough to change what a neutrino is to us. Because once you have caught one, you have more than a number. You have a particle that came from somewhere, that carried its energy in a straight line across the dark, unbent and unblocked, from a source you might yet learn to name. The record breaker in the Mediterranean points back at a violent engine no one has identified. The Blazar neutrino before it pointed at a black hole. Each one arrived carrying in its energy and its direction a story about where it was born. And once you can catch them at all, a neutrino stops being a nuisance that ignores you and becomes something far more useful, a messenger. And once you can catch them at all, a neutrino stops being a nuisance that ignores you and becomes something far more useful, a messenger. To see why, go back to the night of February 23rd, 1987. A star in the Large Magellanic Cloud, a small satellite galaxy about 168,000 light-years away, tore itself apart. It became supernova 1987A. It was the closest supernova anyone on Earth had watched in nearly 400 years, and the first thing to reach us was not light. 3 separate detectors buried on 3 different continents felt it first. Kamiokande 2 in Japan logged 11 events. The IMB detector in Ohio logged 8. The Baksan Neutrino Observatory in Russia logged 5. 24 neutrinos in all, arriving inside a window of roughly 13 seconds, and that burst reached Earth about 3 hours before any telescope saw the explosion's light. Think about that gap for a moment. 3 hours is the length of a long film. For 3 hours, a handful of physicists held knowledge that no astronomer with a lens could yet confirm. A star had died, and its ghost particles had already told us so. Before we go further, a small favour. If this is the kind of quiet you want more of, a like or a subscribe helps this channel keep drifting through the dark, and you can find these episodes on Spotify too. That is the whole ask. Now let the numbers carry you. The head start was not luck. It comes straight from everything the neutrino is. When a massive star runs out of fuel, its core collapses in on itself in a fraction of a second. That collapse releases a colossal flood of neutrinos, nearly all of the dying star's energy poured out in one silent pulse. Because neutrinos barely interact with anything, they stream out of the crushed core almost instantly, as if the surrounding star were not there. The light has a much harder journey. The photons have to fight their way out through the churning, opaque debris of the explosion, scattering again and again. So the neutrinos win the race by hours. That single burst of 24 particles did something no experiment had done before. It marked the birth of neutrino astronomy. For the first time, humanity had detected a violent cosmic event through neutrinos before confirming it by any other means. A whole new sense had opened, one that looks not at how the universe shines, but at how it shudders. For 30 years after that, the field waited for its next great moment. It came in September of 2017. On the 22nd of that month, the Ice Cube Observatory, frozen into the Antarctic ice, caught a single neutrino carrying an enormous amount of energy, roughly 290 trillion electron volts. That is far more energy than the sun could ever hand a neutrino. This one came from somewhere fierce and somewhere far. When astronomers traced its arrival direction, they found something waiting there. A flaring blazer catalogued as TXS Ju506. A blazer is a supermassive black hole with a jet of matter aimed almost straight at Earth, a natural particle cannon pointed at your sky. This one sits about 4 billion light-years away. It was the first single neutrino ever tied to a specific source outside our own galaxy. The story got stronger when physicists went back through the archives. They combed through more than 9 years of stored ice cube data, and they found an earlier signal. Between 2014 and 2015, that same blazer had already sent a flurry of neutrinos our way, an excess reaching about 3.5 sigma confidence. So the object had been quietly flooding Earth with these particles years before anyone thought to look. It had been broadcasting into the dark, and we simply had not learned to listen yet. You may be wondering why anyone goes to such lengths for particles this stubborn. Here is the reason, and it is the whole point. Neutrinos travel in a straight line. Light gets scattered by dust and absorbed by gas. Charged particles get bent and twisted by every magnetic field they pass. A neutrino ignores all of it. It is not deflected by dust, not blocked by gas, not curved by magnetism. It leaves its source and travels an undistorted line straight to you, carrying a signal that has crossed billions of light years without being smeared or bent along the way. That makes a neutrino the most honest messenger in physics. When one arrives from a blazar 4 billion light-years off, it points almost exactly back at where it was born. No other cosmic messenger can promise that. It is like receiving a letter that has passed through every storm in the universe and arrived without a single smudge on the ink. The same honesty works close to home. The sun makes neutrinos as a direct byproduct of the fusion burning in its core. Those neutrinos escape almost the instant they are made, so a neutrino detector can, in principle, watch the sun's core in real time. Remember what that means. The sunlight warming your face right now left the sun's surface about 8 minutes ago, and it spent tens of thousands of years trapped inside the sun before that. A solar neutrino tells you what the core is doing right now, 8 full minutes ahead of the light itself. It is as close as physics gets to a live feed from inside a star. So neutrinos have become a new kind of telescope, one that sees through the walls that stop ordinary light. But for all they have already shown us, the strangest part is what they still refuse to say, because underneath the discoveries sits a pile of unfinished business, and some of it reaches all the way back to the first second of time. Start with the biggest ghost of all. Physicists believe there is a sea of neutrinos filling every cubic inch of space left over from the birth of the universe. It is called the cosmic neutrino background. It formed about 1 second after the Big Bang, when the whole universe was a furnace at roughly 35 billion degrees. As space expanded and cooled over the next 13.8 billion years, that sea of relic neutrinos cooled with it. Today, in theory, it hangs at about 1.95 Kelvin, which is around 456 degrees below 0 Fahrenheit, just a few degrees above absolute zero. By the counting of physics, these relic neutrinos are the second most abundant particle in the universe, outnumbered only by the photons of light left from the same era. They should be everywhere. They should be passing through you as you rest. And yet no instrument ever built has directly caught even one of them. Their energy is so faint, so close to nothing, that no detector on Earth is sensitive enough to register their touch. They may stay invisible for decades more, or forever. There is one thread of indirect evidence. This ancient neutrino sea left a faint fingerprint on the cosmic microwave background, the leftover glow of the Big Bang. That fingerprint is a subtle shift in the pattern of temperature ripples across the sky, and it was reported detected in 2015. So we have felt the shadow of this relic ocean without ever touching the water. Picture it as a second afterglow of creation, not made of light, but of neutrinos, soaking silently through your body while you drift towards sleep. Then there is the question of what a neutrino truly is at its heart, a question physics has not been able to close. Every other matter particle you know has a mirror twin, an antiparticle with the opposite charge. The electron has the positron, but the neutrino has no charge to flip, and that opens a strange possibility. The neutrino might be its own antiparticle. Physicists call such a thing a Majorana particle. No one yet knows if the neutrino is Majorana or not. It sounds like a technicality, but it is anything but. If the neutrino turns out to be its own antiparticle, it would be unlike any other matter particle we know, and it could help explain one of the deepest riddles in all of science. Our universe is made almost entirely of matter, with almost no antimatter left. Something tipped the balance early on. The Majorana nature of the neutrino may be part of that answer, a clue to why anything exists at all rather than cancelling itself out. Experiments around the world are hunting for it right now, and the verdict is still open. There is one more thing the neutrino keeps to itself, and it is close to being solved, but not quite. Physicists know there are 3 flavors of neutrino, and they know these 3 have slightly different masses. What they do not yet know is the order. Is the type most people expect to be heaviest actually the heaviest? An arrangement called normal ordering, or is it secretly the lightest called inverted ordering? This is the mass ordering problem, and it has resisted a clean answer for years. The newest attempt came from an experiment called Juno, which released its first data in late 2025. Gathered over 59 days between the end of August and early November, it sharpened two of the fundamental numbers that govern how neutrinos behave, improving on any previous experiment by a factor of about 1.6. That is real progress. But the central question of the mass ordering is still formally unresolved. The data leans toward normal ordering at roughly 3 sigma. In physics, 3 sigma is intriguing, even exciting, but it is not proof. The bar for a true discovery is 5 sigma, and the neutrino has not yet cleared it. So here is where the story leaves you. A particle that pours through your body by 100 trillion every second, born in the hearts of stars and in the death throes of stars, has already opened a new window on the cosmos. It gave us 3 hours of warning from a dying sun 168,000 years in their past. It pointed us back across 4 billion light years to a black hole's jet. It carries, in theory, the oldest echo of the Big Bang still ringing through the dark. And still it holds things back. We do not know its true weight. We do not know whether it is its own mirror image. We do not know the order of its hidden masses, and we cannot yet touch the ancient ocean of relic neutrinos said to fill the space around your bed. The most abundant matter particle set loose upon the universe remains, in the ways that matter most, a stranger. There is one story about the neutrino that refuses to end, and it begins at a laboratory in the flat farmland of Illinois at Fermilab, with a machine called Mini Boone. The name is almost a joke, a small nod to a bigger experiment that came before it. Inside sat a great sphere filled with mineral oil, lined with hundreds of light sensors, waiting in the dark. A beam of neutrinos was fired at it across the fields. The plan was simple. Count the electron neutrinos that arrived, and see whether the count matched what the known rules predict. It did not match. For roughly 15 years, Mini Boone kept seeing more low-energy electron-neutrino events than it should have. Physicists call this the low-energy excess. It is not a small wobble. Over all those years, the signal climbed to a statistical significance of 4.8 sigma. That number matters more than it sounds. In physics, a result at 5 sigma is the gold line, the point where you're allowed to stand up and call something a discovery. Mini Boone crept right up to the edge of that line and stayed there. On almost any other subject, a signal this strong would already carry a name and a Nobel citation. Instead, it carries only a question mark. So the question became the obvious one. What was making those extra neutrinos appear? And the leading suspect for years was a particle that has never been seen at all. They call it the sterile neutrino. To understand why it was such a tempting idea, you have to remember how little the ordinary neutrino already interacts with anything. It ignores the electromagnetic force. It ignores the strong force that binds atomic nuclei. It answers only to gravity and to the faint whisper of the weak nuclear force. A sterile neutrino would go one step further into silence. It would not even feel the weak force. It would be a fourth flavor beyond the 3 we know. A particle that touches the rest of reality through gravity alone. More elusive than the ghost. A ghost of a ghost. And here is why physicists wanted it to be real. a particle that barely interacts, that drifts through everything, that carries mass and answers only to gravity, is exactly the kind of thing that could help explain dark matter, the unseen mass that outweighs every visible star and galaxy many times over. So the sterile neutrino was not just a patch for one strange result. It was a door that might open onto one of the largest missing pieces in all of science. You can understand why people wanted to walk through it. The excess was tempting for another reason too. Minnie Boone was not the first machine to see something odd. Years earlier, an experiment called LSND, running at Los Alamos in New Mexico, had recorded its own excess of neutrino events that did not fit the standard picture. Two separate machines built by different teams in different decades in different states had each looked into the beam and each seen a few too many arrivals. When one experiment sees an anomaly, you suspect the experiment. When two independent experiments see compatible anomalies, the suspicion shifts. Maybe the machines were not fooling themselves. Maybe nature was trying to tell them something in a language they could not quite read. So a plan was drawn up to settle it. If a sterile neutrino was quietly reshuffling the beam, then a better, sharper detector should be able to catch it in the act, or prove it was never there. That detector was Micro Boone, and it sat at Fermilab too, downstream of the same idea. It used a newer technology, a great tank of liquid argon that lets physicists photograph the tracks of particle collisions in fine detail, almost like developing an image rather than counting flashes. Where the older machine saw a blur, this one could trace lines. It was aimed at the same kind of beam, and it was designed to ask a very specific question. When the excess appears, is it really electron neutrinos arriving, the fingerprint a sterile neutrino would leave, or is it something else wearing that disguise? In 2025, Microboon gave its answer, and it used two separate particle beams to reach it, cross-checking the result rather than trusting a single line of sight. The verdict was clear enough to state plainly: the simplest sterile neutrino explanation, the single extra flavor that so many had hoped for, was ruled out at 95% confidence. The door that seemed to open onto dark matter was, at least in this form, quietly closed. You might expect that to be the end of it. A tidy conclusion. The anomaly explained away, the exotic particle dismissed, the file stamped and shelved. And this is the twist that keeps physicists awake. Ruling out the sterile neutrino did not make the excess go away. The original signal, the extra events that Minnie Boone saw and that LSND hinted at before it, is still there, still real, still statistically stubborn. All that changed is that the most comfortable explanation for it has been taken off the table. Think about what that means for a moment. Slowly. For years there was a mystery and a suspect. The detective work advanced, and when the evidence finally came in, it cleared the suspect without naming replacement. The crime is still on the books. The room is still disturbed. Something entered the beam and left more electron neutrinos than the rules allow, and now the one intruder everyone expected has an alibi. The question did not shrink, it sharpened. This is how the frontier of this field actually feels from the inside. Not a straight march toward answers, but a long argument where each resolution exposes a deeper puzzle underneath it. Every time an experiment closes one explanation, the surviving mystery grows stranger because the easy stories keep running out. And so, having lost the sterile neutrino, physicists have started reaching toward stranger ideas still. The phrase you now hear is dark sector. It is a catch-all for hypothetical particles and forces that do not fit into the tidy roster of the standard model. A shadow set of physics that would interact with our world only faintly, through side doors we have not yet mapped. Perhaps the extra events at Mini Boon were never neutrinos changing flavour at all. Perhaps they were the decay products of some heavier unseen particle, something that flickers into existence in the beam and falls apart into a spray of light that a detector mistakes for a neutrino arriving. Nobody can say for certain. These are candidates, not conclusions, sketches drawn to fit a shape that will not resolve. What makes this worth sitting with, as you drift here in the dark, is how honest it is. The 4.8 sigma excess is not a mistake that got cleaned up. It is a genuine crack. A place where the most thoroughly tested theory in the history of science quietly fails to predict what a machine sees, and where the obvious repair has just been shown not to hold. The people who study this do not pretend to have the answer. They have a real result, a discarded explanation, and a growing list of stranger ones. That is the whole state of the art, an open wound, carefully measured, and it fits the deeper character of this particle. Everything about the neutrino has followed this pattern. It was invented to save a law, then doubted, then found. It was declared massless, then caught changing flavour, which proved it had mass after all. Every clean statement made about it has eventually cracked, and each crack has revealed a larger room behind it. The Mini Boon anomaly is simply the newest of those rooms, the one physicists are standing in right now, holding their instruments, listening. So the sterile neutrino may return in some altered form, or it may stay banished. The dark sector may yield the answer, or it may be another door onto another empty hall. The excess itself sits there in the data, patient, unexplained, waiting for a machine sharp enough or an idea bold enough to name what caused it. For now the detectives have narrowed the field by ruling one thing out, and the case is more interesting, not less, for having done so. That is the strange gift this particle keeps giving. It answers just enough to prove there is more to ask. Every settled question in its long history has turned out to be a threshold, and behind each threshold has waited another mystery, dimmer and more distant, glowing faintly at the limit of what anyone can yet detect. So much about the neutrino is still unwritten, still waiting somewhere in the dark for the next faint flash of blue light. So much about the neutrino is still unwritten, still waiting somewhere in the dark for the next faint flash of blue light. And while it waits, it does not pause, it does not slow. Even now in this quiet room the flood is moving through you exactly as it always has. Let that be the last image you carry into sleep. Not the machines, not the equations, not the long list of things we still cannot answer. Just this. A silent river, pouring through the walls, through the bed, through your chest, through the small bones of your hand, and out the other side into the ground below. Roughly 100 trillion of them every second. You have never felt a single one. You never will. Think about where they came from. Almost every one of them was born in the heart of the sun, about 93 million miles away, in a furnace of hydrogen fusion you will never see with your own eyes. A particle of light made in that same core takes tens of thousands of years to fight its way out. A neutrino made beside it slips free in about 2 1/3 seconds, as if the sun were not there at all. By the time you feel the warmth of sunlight on your face, that light is old news, minutes behind. The neutrino is the true live broadcast. It shows you the core as it is right now, this moment, streaming through you as you rest. And not all of them are from the sun. Somewhere in that river are travellers from much farther away, ghosts from stars that died before there were any humans to watch them die. On a night in early 1987, a small burst of them arrived from a star that had exploded 168,000 light-years away, and they reached us a full 3 hours before the light did. Some of the neutrinos crossing you tonight have been falling through empty space for millions of years, undisturbed by dust, unbent by any magnetic field, a straight and silent line drawn from the edge of the visible universe to the quiet dark of this room. Hold both of those thoughts together for a moment. The messenger from the center of the sun and the messenger from a star long dead. They are mingled in the same flood, moving at almost the speed of light, and they are passing through you at the very same instant. You are the crossing point, a soft, warm, sleepy body lying still in the dark, and through you pours a message from the living core of one star and the last cry of another that ended before your kind existed. You feel none of it. There is nothing to feel. That is the whole strange gift of it. This is the paradox the night has been turning over, and it does not need to be solved to be beautiful. A neutrino is almost nothing, almost no mass, no electric charge, blind to the force that makes touch and light and colour. It ignores nearly all matter it meets, which is why a wall of solid lead a full light-year thick would only give it a coin flip's chance of stopping. That same near nothing is what lets it pass straight through you without a sound. The reason it can cross you is the reason it can carry news from places light itself cannot easily leave. Its weakness is exactly its power. The thing that makes it a ghost is the thing that makes it a witness. And once, perhaps just once in your entire life, one of them will stop. Out of all the countless trillions that stream through you every second of every year you are alive, on average a single one will strike an atom somewhere inside your body and give the smallest possible nudge and be gone. You will never know when. It may have happened already. It may be tonight. It changes nothing you can feel, and yet it is a real event. A genuine collision between you and a particle that has crossed an impossible distance to find that one atom out of all the atoms in you. There is no need to remember any of the numbers now. Let them settle and go soft. The names of the detectors, the depths of the ice, the years and the odds, they can all sink quietly beneath the surface. What stays is simpler than any of it. You are lying still, and you are being crossed, constantly, gently, without harm, by the quiet breath of the sun's core and by the fading voices of stars that are already gone. It has been happening every second of your life. It happened while you were being born. It will happen while you sleep tonight, and every night after, and you will never once be disturbed by it. So let the river carry you now, the way it always has, the way it always will. There is nothing to guard against, nothing to catch, nothing you need to do. The flood asks nothing of you. It only passes through, on its way from the heart of one star to the ground beneath you. Using your resting body as a doorway, it does not even notice. Feel how small that makes the worries of the day, and how strangely held you are inside something so vast and so old. The sun is still shining in its core, and you are inside its light in a way your eyes will never manage. The dead stars are still speaking, and you are lying in the path of their voices. And all of it moves through you in perfect silence, gentle as a tide going out, while your breathing slows and the dark grows soft and kind around you. Rest now, let the silent river run. Sleep well tonight. Good night.